Hi all, this is Mr. Yeager, looking this time at some nuclear physics. For on-level physics, we do some very basics in terms of what nuclear physics is all about. Just looking at essentially where does nuclear energy essentially come from, where is it produced from inside the atom, and then obviously the different types of radiations that come out. We'll also look at nuclear reactions, and then in a separate video we'll look at half-life. So some of this stuff I feel like is again covered back when you did physical science, but now we're looking at this maybe just a little bit more, but not that much. So here we go. So with nuclear physics, as you can see here, we are looking at the nucleus of the atom itself. Okay, nuclear energy always comes from the nucleus of the atom. And so what's inside that nucleus? The nucleus has what we call nucleons. Okay, that's a term that we should know. We use that term a little bit more in physics than in chemistry. And those are the protons and the neutrons. All right. Obviously, as you learned from chemistry, there are electrons, but they're not in the nucleus. The electrons is what helps create chemical energy because they would do chemical reactions. All right, was the main part. So chemistry obviously is much more focused on the interaction of the electrons between different atoms. Nuclear physics is looking at the actual nucleus of the atom, the protons and neutrons themselves, seeing what they will do to release out some energy for us to possibly use in some form. Okay? So what we have inside, since we're looking at this from a physics standpoint, is we're interested in forces. All right? We already kind of know that obviously electrons and protons, they're charged. They're going to be held together by these electromagnetic forces, electrostatic forces in some cases too. All right. The whole idea that we have a positive charge attracted to a negative charge, that's kind of self-explanatory. Again, the electrons don't fly into the nucleus because they're constantly moving. All right. And so it's not like that the protons can pull that straight into it. It's the same idea as basically the protons are like the sun and electrons are planets. The Earth is not going to get pulled into the sun because it already has some motion that's able to continue moving around and around the atom. But there is this electromagnetic force between the two that keep the atom together, the protons and the electrons together. Okay. What about the positive protons and the neutral neutrons? Okay. I mean, if we look at this just from a charge standpoint, one, the neutral neutrons have no reason to be together. All right, there's nothing holding a neutral charge to a neutral charge. And in the same case, the positive charges basically are repelling each other. And the thing is, these protons and these neutrons are packed extremely tightly together. All right, they are forced and they are tight together. So the thing is, from an electromagnetic, electrostatic charge perspective, electric force perspective, it doesn't make sense. Why would they be held together? Because again, from a neutral neutron, there is no electric force, zero. So there is no reason that there's no attraction or repulsion. Positive protons, they're not going to do anything with the neutral neutron, but they should repel each other. So again, why are they all being held together? And what we have is what we call a strong force. It seems very vague, but obviously it kind of makes sense. We must have some sort of strong force, and again, that's the legitimate name, that must be holding these particles together, all right? Because it's not a charge force, it's not a magnetic force, it's not a, it's not a gravitational force. I mean, there's a little bit of that involved because particles do attract from mass, but the thing is, gravitational force is very, very weak, all right? So there must be something else that comes into play, and we have what we call a strong force. And this force is the actual attractive force between proton-neutron, proton-proton, neutron-neutron. All right? So the thing is, what we're saying, and I'll explain that little like circled energy down at the bottom there in a second. What we're looking at here is this force, the strong force, keeps all these particles together. It is obviously stronger than any static charge force that tried to pull them apart. All right, if I did draw like a free body diagram, basically the strong force would be pushing the particles together, and then obviously with the protons at least, an electric force would be trying to push them apart, but the strong force is stronger. All right, so what this kind of also tells you is that when I pull these apart, when I'm able to break the nucleus I must have energy released from that nucleus, all right? Because basically the force helps create, obviously energy does work, and so if I want to break this, there must be a release of energy as well, okay? And again, it results in the particles actually being happier together, lower energy when they are together than if they are apart. That's the other part as well. So again, it takes us back to chemistry. Chemistry is all about finding the lowest energy possible. And it turns out that this situation, the protons and neutrons being close together, is more energy beneficial. And that's why it's so difficult to break them apart. That energy is going to be released. All right. So, how do we basically break apart this atom or put it together? Okay, splitting or fusing the atom. What makes it stable? All right, and that's what we're going to look at some. What is the nuclear stability? All right, and so what we have is basically what happens is these atoms will release radiation. Radiation is just another term for energy. Obviously, it has that connotation of being very dangerous, but light is radiation. Okay, the visible light is radiation. It's just an energy that's not dangerous to us. All right, and so what happens is this energy gets emitted by the nucleus to help stabilize it. All right, maybe as it forms or maybe as it splits, and this radiation is going to be released to form the appropriate size nucleus. So there's a greater stability as more radiation gets, as the radiation basically, oh sorry, there's more stability as you don't have the radiation being emitted. Radiation being emitted basically means those particles are still shaking a lot, all right? And so therefore, if I releases some of that radiation, it probably rearranges itself, and then it finally finds a point where it's perfectly stable, okay, where it's not going to continue releasing this. So again, what I'm referring to here is whether it's splitting or fusing, that radiation release kind of tells you how stable the atom is. More radiation, less stable. All right. So it turns out that iron 56, and what is 56? 56 is the mass number, and we'll come back to that a little bit later again when we look at the protons and, well, minus this, we'll say it. 56 mass number, if you recall, is the number of protons plus neutrons. Let's just say that right now. Okay. So it turns out that iron 56 is the most stable nucleus in the universe. All right. What that means is it's going to release very, 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 very little radiation. Obviously, basically almost undetectable. All right. But what we're saying is it turns out, for whatever reason, that number of protons and neutrons is a highly stable number, a highly stable nucleus number for atoms. And so what happens is anything smaller than that basically loses energy when they become larger. Okay, what we're saying is Fe56 is the most stable. So anything smaller than that actually will lose energy as it becomes larger. Atoms larger than Fe56 will lose energy as they become smaller. Okay, and so what we're saying is, again, when I'm going to get into fusion and fission, all right, larger atoms, when they split, will release that radiation, and as they become smaller, become more stable. On the other hand, those smaller atoms, as they continue to become larger, basically can lose some energy. Again, it has a lot to do with the proton-neutron ratio that Fe56 has developed, but there's different things that can be involved to help you figure out whether to fuse or split the atom. We don't get that much detail with it. Okay? So here's your two big processes, fusion and fission. Okay? Fusion, obviously the word fuse is inside of it, means that the atoms are combining. The nuclei themselves are combining. Not just the electrons, but the nuclei. We don't care about the electrons. All right? That they are combining to form a larger nucleus. So small atoms generally can combine, and we can force them to combine to become a larger nucleus and possibly even become more stable than what they were. Fission is the complete opposite. This is the splitting of the atom, causing it to become smaller. So fusion and fission. Right? Where do these processes occur? Stars produce both fusion and fission products. Basically, they have enough heat and energy that they are these amazing reactors, obviously, in space, that are busy actually creating all the natural elements in the universe. Every single natural element that is on Earth originally came from a star. All right, that is a supernova star. All right, because it's been able. I mean, the majority of a star is hydrogen and helium. But what it'll do is it'll keep on putting those, stacking them, sticking them together more and more, creating a larger element. That larger element then gets bombarded by more hydrogens, becomes larger, and vice versa. If some of those elements become too large, basically it splits back up and goes back to a smaller element. But all of those elements are then released into the universe during a supernova. Okay, so again, that's what we basically have here. These elements are then combined through gravitational force and other forces to then basically become our planets, additional stars, and additional comets. Okay? So it's an endless cycle, fortunately. All right, this takes us back to some chemistry. Isotopes. Isotopes are these atoms that have the same number, sorry, I can't talk. Isotopes are atoms of the same element, but with a different mass number. In other words, a different number of neutrons. So you might be asked again questions about this in terms of just being able to identify the number of protons and neutrons in an atom. If you recall again, as we did already, whenever we write out an atom like this, where it's a element dash 1, this is the mass number. Okay? And the other part that people probably forget is we also have atomic numbers. And atomic numbers is the number of protons, which then basically tells you the type of element you have. The atomic number is your social security number. It tells you that you are you in that particular situation. Okay? So the number of protons is the element. So the thing is, all of these elements are isotopes. That means they're all hydrogens. So they all have the same number of protons, which turns out to be 1, 1, and 1. Okay? But the thing is, they have different mass numbers. They have different number of neutrons. So this number, this 1, has to be 1 plus what? 1 proton plus how many neutrons equals 1? That's 0. Okay? How many for the second one? This is a mass number of 2. This would be 1 plus 1. Okay? 1 proton, 1 neutron. And then the third one, H3, would be 1 plus 2. All right? It's the number of neutrons that change, not the number of protons. Obviously, when you took chemistry, some people struggle with that. They always change the protons, but when you change the protons, you have a new atom. I always start off, if I'm given a chart like this, I always start off by writing all the protons out, and then basically you just subtract from the mass number. 1 minus 1 is 0. 2 minus 1 is 1. 3 minus 1 is 2. All right? But that's isotopes. I feel like you should already know that by now. All right, here's another example. We have uranium-235, 238, and 239. If I look, and again, you'd be given some sort of periodic table, so you don't need to know these off the top of your head. But uranium has an atomic number of 92, so that's the number of protons. So all 3 of these isotopes have 92 protons. And then I basically have to subtract that to get the number of neutrons. So 235 minus 92 is 143. This one would be 146, right? Yep, 3 more. And this would be 147. Okay. And that's where we would get the protons and neutrons. Again, very clear. The number of neutrons are different, but the atoms are the same. All right. Basically leading us to essentially our last 2 topics, radioactive decay and then nuclear reactions. So we already talked about it a little bit. Radioactive decay is this process of releasing radiation, releasing energy to form a new element. All right. When something releases radiation, it is most likely releasing some of the protons and neutrons to become a new element. And again, it's coming from the nucleus of the atom, not just the surrounding, from the nucleus of the atom itself. So what we're interested in is what types of radiation are there. Okay, so we got a little chart here, and I'll try to make sure this is clear because some of that might not be clear at the top. We have basically 3 types of radiation: alpha, beta, gamma. But just as a star, as it says over here, you will also see in nuclear reactions where neutrons are released. All right, neutrons are not radiation. All right, they are just a particle. But the idea here is basically, you know, where you almost throw a bowling ball at the pins, and then the pins are the nucleus, and different parts of it are going to split out. That's what we're looking at this particular point. So alpha, beta, gamma are different types of radiation. They are energies. In this case, though, it's kind of interesting because a couple of the energies, top radiations, have some sort of mass with them. Some. Okay? So what you need to know about all of these is you need to recognize their symbol. This is charge. I'll rewrite that. Mass. And then I like to add in what's the danger from them. All right. When I say danger, I'm going to talk about what you need to block that type of radiation. All right. And you're going to see that I only do that with the types of radiation. If I start with neutron real fast, the symbol for neutron will be N10, and I'm going to explain that on the next slide what the 1 and 0 basically mean. So alpha. Alpha turns out that it's the size of a helium nucleus. So we use that symbol for alpha, 42He. All right. Alpha, because it's basically telling you it has protons and neutrons in it, has a positive charge. Okay, those protons carry the positive charge. It turns out that the alpha will have the largest mass, so I'm going to write large, and it has the lowest danger. Lowest danger, again, this is energy as well. I'm going to write energy. Lowest danger, lowest energy. It can be blocked by paper. By holding up a piece of paper, you are protecting yourself from alpha. Your skin protects you from alpha. All right. The only way for alpha radiation to really get inside of you is you swallow something that then basically starts releasing radiation inside of you. Not recommended. Beta. As for beta, all right, it looks like it's the symbol for electron. If you again you recall from chemistry, E, but it has a -1 proton charge, okay, which is weird. And again, I don't want you to think it's a proton. It's not. But it basically is going to create a -1 charge to the atomic number. And so this has a negative charge. I'm going to just say this is small, because obviously it doesn't have nearly as much mass as the alpha particle. And I'm going to say this is basically medium danger. You would need basically like wood to block this, a block of wood. All right. So if you're inside a building, beta is not going to be able to go through. It can travel through clothing and your skin. So this one you'd have to be a little bit more careful of. But believe it or not, it turns out alpha and beta are always being released in the environment by these elements undergoing radioactive decay. But in such low quantities, it's not dangerous at all. Gamma. This is the one you got to be scared of. It has kind of a funky symbol like that, almost like a weird looking Y. It is 0, 0. So this has no charge. It has no mass. Basically, it is pure energy. So it has a very high amount of energy. You will need basically lead to stop this. All right? Just like when you go to the doctor's office, you need to wear a lead vest when you take x-rays. All right? Gamma is going to actually need even thicker lead than what you have with the x-rays. You need multiple layers of concrete, and then, the example of something I've read one time in a textbook was you needed like 2 feet of concrete followed by like 5 feet of a water area followed by another 2 feet of concrete. I'm like, I don't know how you're going to make a house like that. So gamma, unfortunately, is the most dangerous. You'd not be able to be protected by this inside a house, all right? You'd have to basically have it contained within a very, very sealed area, all right, is what you're looking at there. So when I ask questions about this, just make sure you understand all the different pieces of alpha, beta, gamma, their symbol, their charge, their mass, and the danger involved. The neutron, again, you just need to know the symbol because we're about to do nuclear reactions. All right. So to go back where some of these numbers came from so that we understand, because you need to understand this for nuclear reactions. You already saw me write like the one up top here, He-4. Whenever something is written like that, I'm giving you the mass number because I can look up the atomic number for helium on a periodic table. Okay? I can just look that right on up. All right? But when we're about to do our nuclear reactions, we're going to write elements out like this, where we write the chemical symbol. Okay? Again, I hope this is not all new to you, otherwise you're in some trouble. U would be the chemical symbol for uranium. The top number is the mass number, so I'm giving you the mass number again. The bottom number is the atomic number. So this is the best way to kind of write out an abbreviation for an atom because you have all the information now. You know what the atom is. You know the number of protons. Again, that's the atomic number is the number of protons. And then the top number is the number of protons and neutrons. So how can I figure out the number of neutrons? If I just subtract these two numbers, that'll give me the number of neutrons if I need that. Okay? If I wanted to write U like the helium atom up here, it would be U-238. If I wanted to write the helium atom like the U down here, it would be He-42. Okay? The larger number is always on top for every element. So that finally leads us to nuclear reactions. All right? Where you're going to show me basically a reaction, a fission or fusion reaction, and the type of radiation that is involved during a like basically a symbolic form. Just like chemical reactions showed you how chemicals change into new substances, reactants, and products, we're doing the same thing with these. We have reactant nucleants, and then we have product nucleants, essentially. And again, we're going to create new elements. The big thing is we do have to balance this. Now, it's not the same balancing as chemical reactions. All right? What we're going to balance is the mass numbers and the atomic numbers on both sides. The total mass number on the left has to equal the total mass number on the right. So you're going to see how I kind of go through that. And then I have to repeat it. Total atomic number on the left has to equal the total atomic number on the right. So, let's see here. I don't think I have a periodic table. Just a second. All right, so sorry about that. Back real quick here. Needed to get a periodic table available. So we can see we have this reaction. And again, I don't care if you don't understand what like the symbols basically mean. Like Bi is the element bismuth. But we should eventually understand what this means. This is a beta particle or beta radiation occurring right there. All right. So what we have here is basically bismuth is splitting apart. What I'm going to do, this is supposed to be an 83, okay, is I need to have the total mass number on the left side of this equation equal the total mass number on the right side. So if I look at this, I only have one element on the left side, bismuth, and it has a mass number of 214. That means the total mass number on the right side here has to come out to 214. Well, the beta is telling me it provides 0 to the mass number, so this new element that I'm missing must be 214. Okay, it has a mass number of 214, but that doesn't tell me what the element is. The atomic number does. So now I'm going to repeat it. The atomic number on the left, total atomic number, is 83. All right, so it has to come out to 83 on this side. -1 plus what equals 83? That's 84. And so then what I do is I have to go to a periodic table. So let's look at my periodic table real quick. 84, if I can read it. 84 would be polonium right here. Polonium. You can see I'm getting this from calendrew.com. All right. So polonium would be my element. And that's how I figure out my nuclear reaction. You're almost basically always trying to find the missing element or the missing radiation piece. And all it's about is basically identifying the mass number, the atomic number, and then the element. And you can go in whatever order. I could have sat there and said, okay, this side's 83, -1 plus what is 83? That's 84. Again, people mess that up. This is -1, so I basically have to subtract 1 to equal 83 on the other side. All right. So 84 is my element. That's polonium. 214 is the mass number. It just follows along with that. You don't get any of these numbers from the periodic table. Okay. All you're going to get from the periodic table is the element itself right here. Okay, so be aware of that. All right, as for the second one, we have iron and helium. I believe this is helium. It might be an alpha particle. It doesn't really matter. But you can see it's releasing a neutron while these two elements combine. All right, so what do I have over here? I have a total mass number of 58. I have a total atomic number of 28. I mean, again, pretty simple addition. That means on this side, I need to have 58 for the mass number and 28 for the atomic number. And if I look at this, 1 plus what is 58? This would be 57. And then 0 plus what is 28? That's 28. I have to look up that element. 28 is 28. Nickel. It is nickel. Woo. Okay. And that's how I can figure out my different nuclear reactions. And that's it. Then you're done. You don't balance anything after that. All right. That is it. All right. So thank you very much.